All right. Thank you. Thank you, Adam. I'm Sanjay Shakkottai. I'm a faculty member here in the EC department, and I work on diffusion models. I'm also the director of the Center for Generative AI. And today I'm going to be talking about discrete diffusion models for image and language generation. So this is based on a series of papers, which is led by Litu Raut. He's a graduate student here, and in collaboration with my colleague Konstantin Karaman at UT. But there are also several other groups who I've worked with closely and want to acknowledge them. Nathaniel Ruiz and Abhishek Kumar from Google DeepMind, Yuzhua Chen, Andreas Lugmeyer, Yasamin Jafarian, Srivatsan Varadarajan, Ira Kemelmacher Schleiserman, and Vincent Chu, who are all from Google. And so these folks are from the Google Pixel team, the Google Imagine and YouTube teams, and from the Google Shopping teams. And this collaboration has been very fruitful, and I'll talk about some of the work with these groups. So in terms of sort of diffusion models, especially for image generation, they are the model of choice and state of the art today for high-resolution image generation and various applications of that. So these models have, over the last several years, have really scaled up from sort of 1 billion size stable diffusion to sort of flow models, which are very, very closely related to diffusion models, which are about 10 billion size and are the model of choice today. And these models are being used for a variety of downstream tasks, starting from text-based editing, meaning you give a paragraph of text and you want to generate an image. Okay? That's text editing. Or image denoising, super resolution, motion deblurring, especially useful in camera pipelines. So you've got this image of a blurry dog, and you want to clean this up. Or there's an image with some part missing, and you want to fill this up. Or even personalization and stylization, meaning I have a picture of my dog here, and I give this other image of a rose and in this style, and say, generate an image of this dog in that style, and you can do this. All these are sort of, once you have a really powerful foundation model, you can do all these kinds of things, which are technically called posterior sampling. Basically tilting the distribution to satisfy both your measurement or require constraints, as well as sort of using the generative model as a prior to make sure that what you get are natural images. And the underlying technology for all these things is based on continuous diffusion, meaning you take an image, you smoothly noise it, and I'll be a little bit more specific later, and then learn how to denoise this smooth noising. Okay? And there's a very, very large community all over the world who have done amazing work in this space and have really advanced this field. So in the next few minutes, I'll talk about some of our own work in this space, but then I'll quickly switch to sort of where I think things are moving, which is the discrete world. So over the last few years, we have been working closely with the Google teams to do image stylization and image editing, both for diffusion models and for flow models. And these algorithms have now been productionized on sort of the Google Pixel phone, on the tablet, YouTube, as well as in Imagine and other platforms. So examples of the kinds of things we are now able to do using these pipelines is the following. So I just talked about it briefly previously. Let me just expand on that. So suppose you're given an image of this, a melting gold rose, and an image of a dog, a single image. Then during test time, without training, what you'd like in about 30 seconds time on a A100 class GPU is to generate an image which merges these two. And this is the kind of thing we want. So that dog in a sort of different layout, meaning the face is turned around differently, but in this particular style. So this problem is called content style composition, and you want to do this at scale, which is 1024 by 1024, and do it really fast. So algorithms for doing these kinds of things, as well as sort of implementations at scale, is something that we have been working on with Google folks. The other example of these kinds of things is style interpolation. So you give this sort of this particular graffiti style image and this glowing mushroom style, and say you want to generate a tiger that interpolates between these two. Now, there is no example where you have an image of a tiger which combines these styles. Nevertheless, during test time, again with order of 30 seconds time scale, we're able to generate images that combine these two. And these things are very useful. You can imagine for various applications and indeed have been productionized in these platforms I talked about. The other side of the story is really lightweight algorithms. So if you want to run something on a Pixel phone, you can't afford to even take gradients. Where gradients come in is in these kinds of pipelines the following, that if you are given some measurements, I give you some text or some coarse image, this is my measurement, and you say, I want to clean this up. Typically, the standard pipeline is to use that as an anchor and sort of take gradients with respect to some loss associated with this. In these kinds of lightweight devices, it's sometimes very hard to do any gradients, and you want to completely do flow-based algorithms. And we developed sort of flow-based image editing techniques. For example, you take a picture of this cat and say, I want a silver cat sculpture. It can convert this to this new image. Or you can cartoonize now. Again, all this is in less than a minute time scale. With the gradient-free things. So these are the things that we have been working on over the last several years. And the underlying technology, as I said, has been based on continuous diffusion or closely related flow models. And the idea is essentially the following. You start from a clean image prior to train a model, and then gradually and smoothly noise it till you get pure Gaussian noise. And then you learn to denoise incrementally, a little bit at a time, starting from this image that just starting to appear to something which it has appeared a little bit more, and then a little bit more, and so on. So once you have trained such a model, this is your generative prior model, and then you can start doing all sorts of fun things with it, meaning you use this model as a prior and say, hey, I want to now start doing stylizing. I want to do something else. But this is your foundation model you start with. Okay? And so in the first slide, when I talked about 10 billion size models, these are the models that the larger community has developed, and many are open source, which has really allowed algorithms at scale from everybody in this community. But there are early indications that a technology shift is starting to occur, and this technology shift is that a discrete diffusion model instead of a continuous denoising model as this. And so what is a discrete diffusion model? It's essentially the following. In 2 words, it's tokenized plus diffuse. And I mean the following by that. So say you got this sentence, a cat is playing with a dog. Okay? What you would do is break this up into tokens, words, or parts of words. And so you can, just like any language model, you construct a sequence of tokens. And once you have this collection of tokens, you can arrange it in this figure. I've just arranged it as a square, where each little square is a token. But you can think of it whichever you want, a vector or a matrix or whatever. For an image, similarly, you can take a particular image and break it up into small patches, so little pieces of this image, and then tokenize that in some way. All that tokenize means is that each one of these elements is no longer a continuous object, but a discrete object in a vocabulary. In the language, say if you have a dictionary about 50,000 words, then each one of these would be simply an integer which is sort of between 1 and 50,000. In an image, each patch would be somehow converted to, again, you create a dictionary, typically of size 10,000, and each one of this would simply be an integer of between 1 and 10,000. Okay? So what you have done is whether a text or image, whatever the modality, you have converted it into a discrete sequence, and you can arrange it as a matrix, you can arrange it as a line or whatever. Okay? And so this is your first step. This is called the all unmasked state, because every one of these tokens are visible. And then what you do in the diffusion is, the most popular diffusion model is to mask them, meaning for each one of these, at some random time, just cover it up, which is basically call it a mask, which is just a new word in the vocabulary. So eventually, what you're going to end up with is everything which is masked. That is your final state, as opposed to in the previous slide, where it was just Gaussian continuous noise. Okay? So it's just erased. And then, once you have that, the discrete diffusion model is learned to unmask things. So that's what discrete diffusion, instead of sort of denoising, it's an unmasking model. So why do you do this at all? First, because it's working in a discrete space, potentially it's much faster inference, meaning you can generate high-quality samples, whether image or language, in significantly fewer reverse steps when you're going from all masked to all unmasked. The second advantage, it provides much finer control. So in a discrete diffusion model, you are working at the level of tokens. Tokens are masked, and the way it's actually represented internally is through a categorical distribution. So if you have 50,000 words, simply each token is a vector of dimension 50,000 with a probability corresponding to, do you think the word is the? Well, it's 0.1 maybe. Do you think the word is synology? I just made up this word. Okay? It's something else, and so on. So it's a categorical description for each one of these. And so you have much finer control. And this finer control also translates to easier posterior sampling, meaning I give you some measurements, and I want to control your generation to get to those measurements. Because this control is at such a fine level, you can do that. You can do much finer level control. For example, maybe I'd like to just take my picture, put a shirt with maybe one button unbuttoned. Can you do such level of control? And these models make it much easier to do those kinds of things. Okay? So this is the benefit of discrete diffusion model. But there are some major challenges. First is that there's a lack of smoothness. Remember, the model is masking. So what you're doing is, at some point, there was a word, and then at some point, it completely disappeared. It wasn't that it was gradually being lost. It is gone in one step. And so this sudden loss of information makes demasking, unmasking, much, much harder. And the second problem is that you're operating in discrete space, so guidance is missing. So gradients are very, very powerful way of sort of moving a noisy image to a clean image. If you're working in a discrete space, such gradient, there is no gradients. It's all discrete alphabet as opposed to continuous systems. So it's much harder to modulate these kinds of things. So even though this is a sort of a very exciting field, there are still big performance gaps in terms of generated text quality with respect to autoregressive models, which is the standard large models today. And for images, it's not clear how to do posterior sampling at high scale. At smaller scales, you can do sampling-based approaches, but as you scale those up, those become computationally really hard. It's not clear how to do that. So that's basically where we are today. So what I want to talk about today is an idea called anchoring, which helps address these questions. So before I define anchoring, let me start with an example. Suppose you had this sentence, a cat is playing with a dog. Okay? And I tell you, if I told you that I'll give you some of these words, will it help sort of decode the rest of it? If I tell you there's an A and an is in the first and the third position, it's not very useful. Okay? These are not very informative words. There are so many other things. But if I told you somehow cat and dog are there in these particular positions, well, it makes decoding the rest of it much easier. So anchors are essentially tokens or soft tokens in general, some distributions over what you think these things are, whose inclusion as conditioning, meaning you know these things, yields a substantial reduction in the conditional entropy of the remaining tokens, meaning it makes things much easier to decode. I'll give you one more example of what this anchoring thing is. So this is from the grade school math 8K dataset. So the math question is, Janet's ducks lay 16 eggs per day. She eats 3 for breakfast every morning and bakes muffins for her friends every day with 4. She sells the remaining at the farmer's market daily for $2 per fresh duck egg. How much in dollars does she make every day at the farmer's market? Now, if I had to give you a few words from this, which will help anchor this whole sentence, it makes sense that the numbers 16, 3, 4, and 2 are much more useful than to know that it's for breakfast, or they're muffins, or it's at a farmer's market. Those things are irrelevant for answering this question. So in this case, the numbers would be the anchors. So again, anchors are those words in this vocabulary, which if you knew, would help decode the rest of things much faster. Similarly for an image as well. There are background tokens, and there are foreground tokens. It's clear that parts of the foreground are much more useful to know than the background, if I had to give you a few things. Okay? So what anchors can do, if you can guess these things, is going to make the decoding process, quote unquote, much smoother. Okay? Because the amount you have to, in the information sense you have to sort of learn is much lower. So anchors are a sort of smoothing mechanism and will address these challenges. So in today's talk, I'll talk about about anchored diffusion language model, but there are 2 ways you can do anchoring. The first is you could use anchors for doing discrete diffusion models. And the ADLM, which I'm going to talk about, is sort of the first DLM that generates better human-like text than autoregressive models at the same scale. And the key idea there is how anchoring decreases this information loss. But you can also use anchoring for image generation, and this is something we recently just completed with the Google Shopping team. So if you want to use a discrete model for high-resolution images, so the problem would be the following. I'll give you this sort of slightly blurry image of this bird and say, generate a high-resolution image of it with discrete space. Not the continuous Gaussian model, but sort of the model which I talked about previously, where patches are just represented as integers, and that's what you're diffusing. So what anchoring basically says, important things should be used to actually decode the rest of it. So first we'll look at how a standard discrete diffusion model for images would how would it generate an image? If you ask, just generate an image, or a high-quality image, if you notice this image, this particular one, you see that first, the easiest things, where it has the highest confidence, is decoded first, which is the background. They're very easy to figure things out. And then it moves to the center. So if you look at that image carefully, you'll see how the unmasking process is happening. Okay? Whereas this end is the anchored model. This image is used to generate anchors, and if you see what happens, it's much later on that actually anything starts to happen. But when things start to happen, it happens much more quickly, and what it generates are sort of the foreground, and once you know the foreground, the rest of it can be filled in very, very quickly. So that's really what anchoring can do. I'm not going to talk, so this is the first sort of gradient-like guidance through anchoring in discrete embedded space, and it enables training-free and test time optimization. As I said, we have worked closely with the Google Pixel team, and so, but I'm not going to talk, I'm happy to talk about this offline, but the rest of today's talk, I'm just going to talk about anchored language model. Okay? So sort of switching gears, so this was sort of the overview. And so let's switch gears to actually talk about the anchored model in detail. So diffusion models have been, as I said, with this overview, it's been used we saw in images and language, but it's also been used for video, audio, and there's a community who has started thinking about diffusion models for language. Some high-profile examples from this year are Gemini Diffusion, or Lada, or Mercury, which was from Inception Labs. And early examples seem to indicate that these can be more accurate. And the reason diffusion models can be more accurate for languages is that unlike autoregressive models, which are generating one token at a time, a diffusion model tries to generate the whole thing in one block. Okay, it starts from all masks and tries to sequentially unmask it without a notion of causality. It doesn't care that the next word is following from these. So this fundamental out of order can help sort of deal with long-range dependencies much better. It can also be much faster because it can decode multiple tokens once it thinks it knows what it is in one stop. It's not forced to just deal with one token at a time. Okay? Of course, there are major problems which we already talked about. But this tells you a history of diffusion language models. So in 2021, D3PM, which was out of Google, was one of the early mass diffusion models. In 2022, you can see the number of papers already ballooned. And about 2022 and 23, you can see the same number of models. By the time you get to 2024, now the timeline has shifted. Now we are talking about 6 months at a time instead of sort of a year at a time. And you see the scale, the number of models that are out at that point is already sort of doubling. And by 2025, it's just exploded. Now we are talking about the quarter time scale. This is the first 3 months. This is the next 2 months. So there's a lot. The point of this is that there's a lot of excitement. There's a huge community developing around these discrete diffusion models. And which is why I think this is potentially, because of the advantages, the challenges will eventually be resolved. And this is something we should pay serious attention to, this class of models. Okay? So again, in terms of, I talked about why discrete models broadly, but now why diffusion language models. 3 reasons. First, because you can do parallel inference. that tokens can be generated in parallel, not sequentially. You can basically, there's hope that you can make it significantly faster for long sequences. The second is flexible editing, because now you're no longer forced to reason from left to right. You can decode wherever you think is important, and this out of order is useful for things like rewriting, infilling, and so on. And again, this also is useful for reasoning, because you don't need to worry about left to right. You can start thinking about what is important in this whole thing, start from there, and then fill the rest out later. This is really why language as a diffusion is an exciting prospect. And in terms of the landscape of these models, so there are sort of, I talked about one type of a discrete diffusion model, which is, erase, which is mask. You have words which are, from this dictionary, and then you just erase it at some time, and then try to figure out what you erased. That's called masking, and there's a bunch of models starting from D3PM, SED, MD4, MDLM. These are from various groups. SED is out of Stanford, D3PM, MD4, and MDLM are from Google, and so on. There's also uniform diffusion models where you don't mask, but just randomly flip or change. You do a random walk on this dictionary, essentially. If a word is an integer, you may just randomly change it to some other integer. You're flipping words, essentially. There are these kinds of models. There's a whole line of work on that. You could try to combine these two, which are mixed diffusion models. You could also say, I don't want to do purely diffusion. I could do diffusion with autoregressive, meaning I can generate a block. I can say maybe anyway from 16 tokens to maybe 128 tokens as a diffusion model, and then auto-regress on top of it. You could do those kinds of things. Or you could actually then say, no, I want to just do everything in continuous space anyway, and then find some way to translate the continuous things using some encoder and decoder to take these continuous vector embeddings and actually translate that into words. And people have tried various approaches. By far today, the state of the art is mass diffusion models for various reasons. They're giving the best performance. But this is not to say that maybe next year some of the other models will come back up. But for the rest of the talk, I'm going to talk about mass diffusion models. Okay. So how does this mass diffusion models work? Well, suppose that at some point while you're diffusing, you are at this particular state. This word is known. It's already unmasked. There's a mask. Something is masked. Then there's with, and there are two masks. Okay, and you want to figure out the next thing. So you go through a denoising transformer, which has been trained. I'm just talking about the inference pipeline. We'll worry about training later. Okay. It'll go through this transformer, which will then predict that the word playing maybe needs to come here. And how does it decide that? It knows that A, is, and with are already decoded. And using this, it predicts some logics internally, which when sampled, will tell you that this thing needs to be playing. So the important thing to note is that it unmasks using already unmasked tokens. That's really what a mass diffusion model does. So you can sort of in sort of the stylized picture here, just mapping what I talked about previously. It means that you are at some point here in this process, and you want to get to this point in the process. Okay. But the forward process to train this denoising transformer is through starting from training sequences which are all unmasked, sequentially mask it, and try to unmask each one. Okay. I'll skip the math, but it's trained using essentially a cross-entropy loss. The challenge with mass diffusion models is that in terms of that the performance gap, it's significantly worse in perplexity and text quality than AR models, even at the same scale. And one of the reasons is this important token problem, which is that random masking will drop sort of key things. In the sentence, a dog is playing with a cat, if I lose the word dog and cat, I lose a lot of information in a sort of, I'm trying to reverse that. Okay? So how can we sort of get around this? So our approach is to develop a different architecture and a training loss, which is our anchored diffusion language model. The idea is the following. So we start from the same thing. A mask is mask with mask mask. That's where we are. So instead of trying to predict the next token, we have an anchor transformer that predicts anchors. What are these anchors? These are soft tokens, essentially distributions, where it thinks what are important. The important things could be what is important is not necessarily only for that position, but for anywhere in this sequence. For example, in this case, so the word cat seems to be high. In this case, there is various logics seem to have similar probabilities. And in this one, the word dog seems to be high. But it's basically distributions where it thinks what is important. How you train this, we'll come to that later. Right now, I'm talking about the inference pipeline, meaning suppose you had this device this transformer could predict such important tokens. What would you do with this then? Once you have these important tokens, then the denoising transformer will generate the next sequence. Okay? And the important thing about the denoising transformer is it does not even care about what is masked or unmasked. It looks at the sequence of important tokens, which are soft reasoning tokens you can think of, and decides what to unmask. And so essentially, because cat and dog is important in this sequence, it says that likely to be playing, and that's why the playing will be generated. So to summarize, so anchors basically have three properties. For tokens that are already unmasked, it continues to keep peak around their true distributions. For tokens that are masked, corresponding to what it thinks are important tokens, it will peak at what it thinks those important words should be. And for tokens that are masked, corresponding to those that it doesn't think are important, it will roughly have a flat distribution. But that doesn't matter, because to decode even those things, it's anchoring on the important things in the whole sequence. Okay? And so you can essentially anchor predictions, influence all the denoising of the tokens. And so it's essentially a latent reasoning space is what you can think of. So the way it differs crucially from other reasoning models is its supervised reasoning. And I'll talk about what I mean by supervised reasoning in just a slide. Okay? So, but to see sort of, these are all cartoons. If you want to look at a real example, we have here's sort of snapshot of a standard mass diffusion language model versus an anchored diffusion language model at a very early time step. So let's look at sort of the mass diffusion language model. So if you look at the kinds of words it has decoded, it's like other, in, were. So words which are easy to decode because they're high confidence. They're likely to occur. It's high probability. Confidence-based unmasking gets that. Whereas anchored diffusion model goes for it tries to predict anchors, and so it tries to go hard for keywords first, and if it indeed gets keywords well, it can be much faster, because anchoring on those, it can get all the other things much faster. And so if you look at the same time step, you can see the kinds of words that are there are sort of more complicated words, like trusting and committee and security are the kinds of words that are coming out of this. So this is qualitatively, you can see the difference in this. Okay? So we have talked about the inference and sort of how these things look. So let's now talk about how do you train this model. So I've put the same picture before. There are these some masked, some unmasked words. There is the anchors, which are soft tokens in a latent reasoning space, and you've got the decoded words. And so what the key ideas are the following. You want to create a loss function which can be train both the denoising and the anchor transformer in a single end-to-end differentiable framework. That's one thing. And the second is to supervise this thought. And the supervising is based on important anchor predictions. So how do you do this? Well, first we need a notion of anchors. So while training, you have a sequence. You have a sequence of tokens. Say a cat is playing with a dog is your training sequence. That's your X. As a pre-processing step, we will extract anchors from these and append it to it. We'll call those Y. So there are several strategies for constructing such anchors. For example, in a language model, you could simply look at low-frequency words as anchors. So look at words which appear less than 5 times, for example, in a sentence, and just call them anchors. So really what you want, recall, is anchors are a small set of words which, if you know, would help decode the rest of it much easier. Mathematically, it's conditioning variables which yields a substantial reduction in the conditional entropy of the remaining tokens. So A heuristic is simply low-frequency words. For math reasoning, it could be numbers as anchors. For logical reasoning, just extract the verbs and nouns and make them anchors. Okay? Or you could actually use a different language model to pre-process to create this data set, this anchor, to sort of append to your actual sequences these anchor tokens. So once you have that, you can train it in the following way. Okay? So the standard denoising transformer, the way you sort of train it is through cross-entropy. So here's a sentence: a cat is playing with a dog. So for any unmasked word, so this, and this are unmasked. So this is this position, this position, this position, and this position. So your system predicts some words and see whether it's cat or not. And based on that, you have a cross-entropy loss. Because these are all categorical variables, you can put a cross-entropy loss. So far, there's nothing new. This is exactly how you would train a standard discrete diffusion language model. But the addition is the anchor. So we supervise the prediction of only the important tokens. So in the training, remember, we have already, the pre-processing says cat and dog are important. So you train anchors on those anchor positions to try to force it to put high probabilities around cat and dog at those positions. For the rest, there is no training cross loss at all. So the new anchoring loss is a sum of two terms, which is one for the regular denoising, regular cross-entropy, plus only for the important tokens because of the anchor pre-processing, a supervision there. That's all there is to it. There are some very nice theoretical properties of this, that this is actually can be interpreted as a variant of an elbow and so on. I'm not going to talk about the theory side of it, but I'll talk about how much time do I have left, Adam? Because I've sort of lost track of. Okay, that's great. Okay. Since I have 10 minutes, I'm not going to, I'll give you a summary of sort of what mathematically we can show. First of all, anchoring leads to efficient training. And this is very, very simple to see. Suppose you truly believe that language is simply just as a graphical model, meaning there are few words which are important, and conditioned on that, the rest are rest can be written as conditionally independent products. So then, in which case, you can easily show that anchoring essentially leads to exponential reduction in sample complexity. And the reason is actually very, very simple to see. If I have, what we are trying to learn, any language model is essentially trying to learn a joint distribution. So you've got tokens x1 through xl, and you're trying to learn a joint distribution over x1 through xl. If you don't have any structure, then one natural way to decompose this joint distribution using sort of chain rule of probability is first the distribution of the first token times the distribution of the second one given the first times the distribution of the third one given the first and the second, all the way up to distribution of the last one given everything else. So let's count parameters needed to learn this. This is a function of one variable you're trying to learn. This is a function of two variables you're trying to learn, all the way up to a function of L variables you're trying to learn. Okay? So you need a function which is and already by the time you're halfway through the sequence, they're order L by 2 number of variables. Okay? So it's order L number of variables. And so you're trying to learn a function in order L variables for most of the time. Whereas if you believe that there is a small number of anchors that actually are the right things to think about, then a decomposition would be very different. It would be the first token given the anchors times the second token given the anchors times all the way up to the last token given the anchors. And once you have that, each one of these terms is, if you have only d anchors, each one of them is a function of just d plus 1 variables, which is much smaller. So if you have a supervision method to deal with this, you can see that the sample complexity is going to be dramatically lower. And with the same data, you can learn much better models. Again, presupposing that there are this structure of your data is such that there are few things that actually are important for the whole thing. And we do know, by the way, in language, such things are done. It goes back to Shannon, actually, who looked at entropy calculations of natural language and so on. We know that language has these kinds of things. Similarly with image, you know that certain things in this image are very important for decoding the rest of it. The key thing is, how do you actually extract these anchors? And we gave you some ways of doing these kinds of things. And we have also operationalized how to use that to actually train a model and an architecture to do that kind of stuff. It also leads to faster inference. You can show that, I don't have the time to go through this, but you can show that if you have an anchored model, that there's a higher likelihood of computing maximum likelihood sequences because anchoring essentially grounds and decreases uncertainty from key tokens. Okay? In the interest of time, I'll skip sort of the inference advantages. In terms of experiments, anchoring diffusion language model in terms of generative perplexity gives much better generative perplexity than any of the other diffusion models, and actually comes close to autoregressive models. So these models are trained at our model, and others in this part of it is trained with about 500 billion tokens, and this is trained on Vista, on the Center for Generative AI at UT. And so again, going back to Adam's sort of pitch, we are able to sort of train models at scale and compete with sort of anywhere in the world as technology demonstrators, thanks to having these kinds of facilities here. In terms of downstream evaluations, ADLM is sort of state-of-the-art among all the current diffusion models, and in fact, at the same scale, outperforms autoregressive models on these kinds of on several benchmarks. I'm going through this fast because I think I have 3 or 4 minutes left, something like that. Okay. Again, in terms of generated text quality, similarly, you get in terms of generative perplexity, meaning GPT-2 large as a judge, you're getting state-of-the-art performance. So I'll spend a little bit more time on this. So in terms of MOV scores, MOV is basically it evaluates human-like text quality. And this also came out of IFML. This was an early paper from University of Washington, which is one of our partners. This is Krishna Pilutla and his colleagues, including Zaid Harshawi, who is the sort of senior author on this. So this is now, the MOV score is now essentially the state-of-the-art, the standard benchmark for generating human-like quality. Okay? And so we can look at an AR model and ask what the MOV score is. If it's really true human data, it's 1. For an AR model at this scale, it's 0.76. So where does any diffusion model stay? Diffusion models were much, much worse than AR models prior to our work. And at the same scale of 1024 decoding steps, in the diffusion model, it's number of demasking steps that you need. It is worse than the AR model, but when you double the number of denoising steps, you got better, and if you are willing to pay even more compute, you got even better. So now you have got this knob to start improving the quality by paying computation. And we believe that now that we have a tech demo, as you scale things up, things will, we can actually get things much better. And you can see the difference between any of the other diffusion models without anchoring, and when you start putting anchoring in, what a big difference it makes, sort of reasoning through this supervised bottleneck, essentially. That's really all that anchoring is. Also, in particular, if you look at sort of, to get with sort of the previous state-of-the-art discrete diffusion model, you'll need to get to 4,000 denoising steps to get a performance which is near 1,000 with 1,000 steps. So it's like you're doing things 4 times faster, roughly, because of anchoring. So this is as far as anchoring for diffusion models. But the same idea can be used for autoregressive models. I'm going to just, I don't have time to talk about how to do anchoring through autoregressive models. The high-level idea is you do exactly what we are doing with causal attention instead of bidirectional attention. Okay? But again, you have a supervised latent space, an anchor space, and you can indeed develop a 2-tier autoregressive model which anchors and then does the next word prediction. Okay? I don't have too much time to talk about this fine-tuning, how you actually train it, so I'll skip that for now. But I want to show you the implications of such a model is. That anchoring essentially enables look-ahead planning behavior, meaning the following. Let's go back to this example of Janet's duck lays 16 eggs, blah, blah, blah. How many dollars does she make every day at farmer's market? The standard chain of thought starts with 16 minus 3. Remember, it's going left to right reasoning. Minus 4 equals 9. And then 9 times 2 is 18 and gets to 18. Anchoring essentially is allowing look-ahead reasoning. That's how it's trained. Remember, it's supervised on what it thinks the important words are, which are the numbers. And so what happens because of that? Each chain of thought is sort of possibly more human-like. I don't know whether I want to use that, but it's definitely out of order. It first says 3 plus 4 is 7. Basically, it goes somewhere in the middle, and then says, okay, this is the total number that's consumed. So 16 were there. 16 minus 7 is 9, and 9 times 2 is 18. So it's giving a different reasoning modality for the first time, instead of going left to right. And we think that this is very powerful and can be exploited for other things. We have some numbers to back these kinds of things in terms of scores for reasoning and so on. But in the interest of time, at least the qualitative things I've sort of hopefully conveyed. We have examples in the paper on sort of logical reasoning and so on as well. So essentially, anchors is a supervised latent reasoning through these soft anchor tokens. It first predicts distributions over important tokens via anchor network, and then anchors on these things to actually decode tokens. So I'll stop at this point. Thank you for your attention. Good. So let me repeat the question. His question is whether we will, since AR models have been around for a while, will we shift away from AR models and move completely to diffusion language models? I think there's going to be a combination of the two. So first, this idea of anchoring can be either in AR or diffusion. So it improves both performance. But diffusion's parallel reasoning is a powerful thing as well. So I think but diffusions have its problems. It works in fixed blocks. Okay, you have to pre-decide the block. It cannot be, AR models have some huge advantages, right? Because you don't need to decide the length of the token sequence. So I think eventually you will move to sort of a combination model, which will be diffusion blocks of a series of a substantial size for order of several K, and then auto-regress on top of it. I think that's where things are going to go in very near future, but that's just a guess. Okay, thank you very much.
I'm sure Sanjay will take more questions as we head out and have a quick coffee break, and then at 11 o'clock, Amin Karbasi is here for our first keynote. You're not going to want to miss that, so stick around. Thanks, Sanjay.